to learn everything about embedded systems. So if you want to share your screen, you
Yes,
can get
please.
started. Thank you, Robert.
Okay, yeah, let me see about that. Okay, hello everybody, good morning, good afternoon, good evening, depending on where you are. My name is Robert, and thank you for joining this session on Introduction to Embedded Machine Learning. We'll look at three things in this session. We'll go through an overview of embedded machine learning, and then we'll talk about challenges and applications of embedded machine learning, which is also called TinyML. So we'll start with machine learning because, obviously that's the superset. And we all know machine learning really is learning from data. So what you're doing is looking at historical data and the outcome or the output of that data, and then trying to find a model or a formula that translates that input to an output. That's the generality of what machine learning is. So when you train a machine learning model, what you're really doing is you're extracting rules that will let you go from inputs to outputs. Now, machine learning currently is possible because we've got a certain number of things. First, we've got a massive amount of data. So over the years, we've been collecting data, and the rate at which we collect data has increased exponentially over the past few years. There's also the fact that storage is now cheap. So there was a time when a megabyte of storage cost a lot of money. Now it's relatively cheap. And so we're able to store all of the data that we collect. And then thirdly, we've got advances in compute, and that refers to both CPUs and GPUs. We now have way more powerful computers than we had 20 years ago. The intersection of all three of these, massive amounts of data, cheap storage, and advances in compute, have made it possible for us to train useful machine learning models. Now, machine learning has two phases. The first phase is the training phase, and that's where you bring the data that you have, which has already been annotated, and then you train a model. Now, there are a few things in the training phase. You need to have your compute resources in place. You need to have your data labeled or annotated. And you need to have a numerical representation of the data that you're working with. So when you think about it, computers only deal with numerical values, basically zeros and ones. So whatever you're dealing with, whether images, video, music, there has to be a numerical representation of that. Now, once you go through the training phase, at the end of it, you have a model as your outcome or your output. And that model is what you're able to use in the second phase, which is the inference phase. Now, the inference phase just requires unlabeled data. And what happens during inference is there's a matrix multiplication between your data and that model that you got from the training phase. And so the output, again, is a numerical value, because when you carry out matrix multiplication, what you get is a numerical result, an output at the end of the day. Depending on what you're dealing with, your output could be a tensor, or it could be a scalar variable. Now, everything that I've said pertains to machine learning, but how does it relate to embedded devices? So when you're doing machine learning on embedded devices, your target is a microcontroller in the general sense. Sometimes you have single board computers that are deeply embedded. That's also embedded machine learning, but in most cases, you're dealing with microcontrollers. And when you're dealing with microcontrollers, the only thing you're doing is inference. There's no training on the microcontroller. All of the training happens before you get to the microcontroller. Most microcontrollers tend to be offline for various reasons. If you want to keep them online, they're going to consume a lot of power. But the point of an embedded application is not to consume a lot of power. So they're usually not connected to, let's say, the internet. But in a few cases, and we'll see some of those examples much later, they might be connected to, let's say, NB-IoT or some type of radio that doesn't consume a lot of power, that isn't strictly on the internet, but will let you transmit data when you need to. Embedded applications have strict requirements for low power consumption, and that is another consideration for embedded machine learning. And then there are computational constraints. So microcontrollers are not desktops, they're not servers, they're not able to carry out the same level of computational activity. And that's one of the reasons why when you're doing embedded machine learning, you're only doing inference. Now, in terms of what you're dealing with, particularly during the training phase, it's important to note that machine learning typically refers to the larger set, which you could train a model using, say, TensorFlow or PyTorch, or any other numerical computation library that you so desire. Now, the output of those models are usually, the models are usually large. They're usually really large, but that's not a problem if you're going to be running your inference on the same type of system that you use to train your model. So if you train a model on a desktop or on a cloud system and you're going to deploy it on the cloud system, the size isn't really a problem. And all you have to do is put an API endpoint in front of that model that will serve the inference. So you can take the inputs, launch the model, carry out the inference, and then send back the output. However, when you start to move away from conventional computers and you go just one step down to, say, phones and tablets, you can't take the standard model and put it on those devices. You start to experience constraints, size being one of them. And so you need to start to shrink down your model so that you can put it on something like a phone. And that's where the TF-Lite library comes in. So if you're working with TensorFlow and you know that your target is going to be a mobile device or even a single board computer, then you know that your target is going to be TF-Lite. Then you're going to work with a subset of the operations that you have in all of TensorFlow. You'll leave some out because of the computational requirements that they come with. Now, if you're going to put a model on an embedded system, on a microcontroller, then what you really need is TensorFlow Lite for microcontrollers. That's the smaller subset of TensorFlow Lite that gives you even a fewer number of operations. There are other things that you get when you move from TensorFlow to TensorFlow Lite to TensorFlow Lite for microcontrollers, but all of that will leave for the training phase. Now, TensorFlow Lite for microcontrollers also serves as the library that you'll use for inference when you get onto the microcontroller. So the key takeaway from this slide is that not every model that runs on a standard server will run on a microcontroller. And you need to know that from the very beginning. So let's talk about some of the challenges of machine learning for embedded systems. Now, the first consideration is the fact that you're working with an intersection of multiple disciplines. So first of all, microcontrollers themselves are in the domain of electronics, electronics engineering, computer engineering, that sort of thing. So as opposed to standard programming where all you really worry about is at best the compiler or the interpreter, but you don't worry about the very specific details of the computer that you're programming for. With microcontrollers, you need to worry about the electronics, particularly because your input and output will be replaced by actuators and sensors, and you need to know how these operate. You need to know what they return to you and how you can either read values from them or activate them to do something. There's also the programming component for microcontrollers. Programming microcontrollers is a slightly different paradigm from programming for desktops. You don't have an operating system. You don't have things like garbage collectors or memory management. You have to handle everything yourself. So you need to be pretty conversant with that. And then there's also the machine learning component, which again is two things. There's the training, which happens on a main system. And then there's the inference, which will be running directly on your microcontroller. So you need to know how to program for that inference on the microcontroller. Now, in terms of ML training, you are really dealing with pipelines. And this, again, is not on the microcontroller. This is on a computer, but you have to worry about your pipeline. First of all, you have to collect the data that you need to train your model. And because you are dealing with microcontrollers, the question becomes, what sort of data are you dealing with? Are you dealing with time series data, for example, data that comes from an inertial measurement unit? Or are you dealing with images, for example, data that comes from an onboard camera? So there's a data collection stage. And just as the previous speaker mentioned, you have to worry about data drift. So you have to collect data from essentially the same sensors that you're going to be using at the end of the day. So you can't use two different sensors. You can't collect data for training using a different class of sensor and then use another sensor for inference. You're going to have data drift. Once you're done with data collection, you need to annotate that data. And once you're done, you then need to get down to your model selection. And your model selection is actually saying, what sort of model do you want to use? First of all, it depends on the type of data, right? And the problem domain. So if it's a computer vision problem, if you're going to be dealing with images, what sort of model do you want to work with? Do you want to create a model from scratch, or do you want to use transfer learning? If you use transfer learning, what's your baseline model, and will it fit into the memory of your microcontroller even before you start fine-tuning it? And then when you're done with your model selection, you get down to training, and then you evaluate your model. And it's not a straight line. So the output or the outcome of your model evaluation might allow for you to deploy the model, or it might require you to go back and either choose a new model or retrain your model for longer if your model hasn't converged. Or you might even determine that you haven't got sufficient data and you might need to go back to your data collection stage to collect data, annotate it, and then get back to model selection and training again. And when you're done, you then need to worry about conversion, because first you're training using something like TensorFlow, but you can't deploy that model. The output of a TensorFlow training step is a protobuffer. If you need to put it on a microcontroller, first you need to convert it to a flat buffer, and then you need to convert it to something like a C++ class that you can work with directly on the microcontroller. And when you get down to the microcontroller itself, after you're done with training your model and converting it, you then need to worry about a few things. So like we mentioned, microcontrollers usually do not have an operating system, so you have to do bare bones programming. You've got limited space for firmware. You've got constraints on how much power you can cause the processor to draw. And so that translates to a limit on either how quickly you can carry out arithmetic operations, or even what arithmetic operations you're able to carry out. So all processors aren't built equal. Some of them are able to handle floating point operations. Some of them are not. Some of them are able to handle a certain operation in one step, and some require multiple steps. And so that would translate to just how long it takes to get something done. So microcontrollers are limited in the math operations that they can carry out. Now, even more importantly is the fact that not all microcontrollers support TinyML. So it depends on the instruction set architecture. Some support TinyML, for example, the Arduino that you see on the screen, and some just do not support TinyML. And then you have to find an alternative microcontroller or find an alternative solution to the problem that you're trying to address. So let's look at some applications. And one of the oldest applications is the application of TinyML in smart speakers. So when you think of smart speakers in the home, we have got smart speakers from the various manufacturers. The way that it's implemented is that there is a specific microphone that is listening for a wake word. So the word that you speak to activate your smart speaker is called a wake word. There's usually a speaker that is listening for that wake word. And then there's a dedicated microcontroller that is listening for that wake word. It doesn't do anything else. It's extremely low power. And all it does is listen for sound and then run that sound through a model. And if it detects a match to the wake word, it then wakes up the primary CPU on the smart speaker, and then that CPU can handle the rest of the workload. But that CPU that handles the main workload is always asleep when it's not needed because of the amount of power draw that it has. So that's one application, one of the older applications. Another application of embedded machine learning is in wearables, and we've got all sorts of wearables. You've got them in smart watches, you've got them in fitness trackers and what have you. And these wearables, they're able to carry out activity detection. So depending on the model that you use, they're able to tell when you've been sitting for a while. They're able to tell when you're walking, when you're running. Some of them can detect other sorts of exercises, weightlifting, swimming, tennis. Some of them will even start tracking an exercise if they detect a certain activity for a period of time. So even if you forget to start the tracker at the beginning of your exercise, it will activate. But one of the things I want to highlight here is fall detection. And fall detection has been a lifesaver for a lot of people because it activates particularly when there's no one around to render help. So if you think of old people who are mostly alone, or even younger people, but people who are mostly alone or who are out working out alone and who experience an accident, what happens is that the inertial measurement unit reports all of the motion, and then a model determines that the signature of a certain type of model matches that of a fall. But more importantly is what happens after the fall. So if a fall is detected, but the person hasn't moved for a period of time, the smartwatch is then able to initiate an alert to a caregiver or a relative to say, this individual, if a fall was detected on this individual and the individual hasn't got up since the fall. And so people are able to do something to respond to such situations. So fall detection has been a good example and application of embedded machine learning. Another application is with illegal logging. And so when you think about it, usually logging happens in places like rainforests that are really large and extremely difficult to monitor. It's not possible to have someone monitoring every square meter or even every square kilometer of these sorts of places. But logging, has negative consequences. Usually without things like embedded machine learning, what happens is patrol teams have to go around and discover where something is happening, or they have to wait for things like satellite imagery to then analyze. And usually that's after the fact. That's, usually a little bit too late. With monitoring for illegal logging, what happens is embedded devices can be placed on trees with microphones, and they can listen out for certain sounds that match, whatever equipment is used for illegal logging, whether it's automated chainsaws or whether it's manual saws or even if it's axes. But the sounds that they produce will get picked up. So similar to how the smart speakers work, but this time around, the wake word is a signature that matches illegal logging. And another example is with poaching. And there's something called the elephant edge collar, which is a collar that is strapped on elephants, and it helps with keeping an eye on them. So similar to the logging scenario, elephants in forests get attacked for their tusks. And it's not just elephants, but we're using elephants here as an example. They get attacked, and you might have a situation in which a patrol team gets round, but usually they're too late to stop the poachers. Sometimes what they have to do is wait for satellite imagery as well. But with the collar is equipped with all sorts of sensors. So microphones, cameras if you want, inertial measurement units. And that makes it possible to track a range of situations that the elephants might find themselves in. So the camera, for instance, will let you see the herd around an elephant, and so estimate the number of elephants that you're dealing with. The microphone will let you listen for all sorts of sounds, gunshot sounds, the trumpeting sounds that elephants make, which fall into various categories. They might just be casual sounds that are using to communicate amongst themselves. They might be distress sounds. The inertial measurement units will let you know the physical activity that the elephants are going through, whether they are walking casually, whether they are running, whether they are in distress and making some sort of motion. The gyroscope will let you know whether the elephants are upright or whether they are down on their side. Maybe they've been shot or something. And finally, embedded machine learning is used in lots and lots of places. There are lots of industrial applications for embedded machine learning, things like tracking the health of equipment. So machinery, for instance, they vibrate when they're operating, but the way that they vibrate is different when they're healthy versus when they're getting very close to breaking down. And so with things like anomaly detection, which is another class of machine learning algorithms, it's possible to tell when a machine has been operating normally and then when it starts to operate abnormally, and then maintenance can be scheduled to avoid unnecessary downtimes within a factory. So I've come to the end of my presentation, and I believe we've got time for some questions.
Thank you so much, Robert. Round of applause from my side on behalf of everyone.
Very
so
good.
that was great. Excellent. Really, really nice. So there's few questions in the chat. So I'm not sure if you want to go.
Yeah, just a second while I bring up the chat. Okay. I'm just scrolling back up a bit. Let's see.
Okay, we can start from one to the last one. Can Arduino and
Okay.
TinyML be used for classifying spectral data? That was from
Yes.
Sharon.
Yeah. Are you at the top or at the bottom? But yes,
I'm at the bottom.
spectral data, yes. Arduino, sorry, hold on. Okay, now this is what
Yeah, I
is the
think
minimum.
it's from the bottom to the top, Robert, because we were helping you during the presentations. A lot of was answering.
Okay. Okay, yeah. So can Arduino and TinyML be used for classifying spectral data? Yes, but my favorite question usually is, what is Arduino? Because, you know, there are all sorts of Arduino boards. The more recent Arduino boards they have an ARM processor on them. And so most of them are able to run TinyML. And so you can carry out classification. The more older ones that have the PIC microcontrollers typically cannot run TinyML in the sense of TinyML, which is you know, the TensorFlow Lite for microcontrollers. They might be able to run some other type of model, but I don't have experience with those.
There's few questions about languages. So there's few questions about Python, C++, and maybe if you want to comment on that.
Okay. Is it up or down? So I need to scroll to find it.
It's down. Okay, it's mixed, I would say. Yeah.
Okay. Is that the one that says, hold on, sorry. Is it required to have strong knowledge on electronics to learn TinyML? Okay. Not that, but let me just answer that since I read it out. So when you work with microcontrollers, it's usually a good idea to have a good knowledge of electronics. And that's because the microcontroller on its own isn't really useful, right? Because with machine learning, you're dealing with something, you're trying to collect some data. So you have sensors that you need to work with. And without a good knowledge of electronics, you know, the way that I think the electronic engineering world is structured, you'll usually get hardware thrown at you. Apologies if that sounds offensive, but you'll get hardware and then you get a bunch of documentation and you have to go read through the documentation. And it's usually not computer science documentation or programming type documentation. It's electronics documentation, right? So you need to have a sense of what's going on there so you know how you're going to read your data and process it. So it's usually a good idea.
There's few questions that I think Marcelo will tackle tomorrow about about, you know, other microcontrollers and even FPGAs and so on and so forth. So I think tomorrow we have one session about the hardware, and I'm sure that Marcelo will
handle that. Great.
Yeah.
I see this question. Yeah, go ahead, Marcelo.
No, I'm talking about the last one. It's interesting about asking about applications, maybe with climate or environmental and transportation. I don't know if you have some examples.
Okay.
The last one from.
Okay, let me see this. There was a question about the minimum level of C++ knowledge required to sorry, hold on. Yeah, minimum C++ knowledge that we need to know to make some working demo of ML on an embedded device. So it's interesting because it depends on the approach that you take. So I didn't show any code examples because I didn't want us to spend 5 minutes talking about something that might work on one microcontroller and not work on the next microcontroller. However, depending on what you're working with, there are usually examples for implementing that. Now, remember that there are two levels to this thing, right? There's the training phase, which isn't really a C++ domain. And there's a question further down that touched on that, if I get to find it. But when you do have your model, whatever you use at the training stage will have some example code that you can take and then customize that to have a working demo on your microcontroller. And then, can Python be used to build TinyML models? Yes, in simple terms. Now, here's what I tell people. Truly, any programming language can be used to build a machine learning model. The problem is knowing the end-to-end of it, right? So you're dealing with a massive amount of data. You need to do things like vectorized computations. So without the right language and the right even library, you could be going through a lot and maybe not even finish it. But yes, Python can be used to build TinyML models. Typically, you'll use TensorFlow, which is the framework. And then you'll have to work with both TensorFlow and TensorFlow Lite and TensorFlow Lite for microcontrollers. Now, if the whole paragraph sounds like a lot, that's because it's a lot, because we had an entire slide for that. But the good thing is, I know that Edge Impulse will be demoed tomorrow. And Edge Impulse is one layer. It's just a platform that simplifies all of these things that we're talking about so that you can go past that stage of building the ML model and focus on the microcontroller. Okay, so yeah, there's a question about PIC microcontrollers, and I think Marcello will go into hardware tomorrow, right? So yes. Yeah, so please tune in tomorrow for additional details.
Only a comment, Robert. Tomorrow,
yes.
I think tomorrow and after tomorrow, we will have a lot of. We start with Sean at the beginning of tomorrow, and after we go to Jose will do a complete example of a TinyML construction sync from data collection to the deploy. I talking about hardware and different type of data. So I think people will see a lot of real stuff tomorrow. Today is for only to open their minds.
Yes, fantastic. And so Hadiza Yusuf is asking, are there models that cannot be used on the microcontroller? Absolutely. There are more models that cannot be used on the microcontroller than there are models that can be used on the microcontroller. And that's because most models are just too large. So even models that fit on a phone will not fit on a microcontroller. So yes, lots and lots of models. And so Andrew wants to know, with more recent Arduino boards, do people combine applications in a few languages for one application? Okay, so, applications are different from models. So you can have one application that does a lot of things. Depends on the capability. So maybe if you're thinking of the Portenta X8 in terms of Arduino boards, then yes, you could combine applications into one application, particularly because of the Linux core that you have on the X8. If you think about the Portenta H7, it has 2 processor cores. You're able to run 2 applications that do different things. So you could have one application that is dedicated to reading something like a speaker or some other sensor and just collecting data and throwing that into a buffer. And then you could have another application running on another core that is just dedicated to running the ML model. But if you're thinking of one application running multiple models, then again, it depends. It depends on the complexity of the application. Because remember, really, a microcontroller is meant to do one thing, right? A microcontroller is not a single board computer. It's not a desktop. So you always need to bear that in mind. Okay, so I see this question about implementing ML on Arduino, but I also see there are some comments there. But the long and short of it again is, and this is for Pape. So Pape, remember, Arduino isn't one thing. There are all sorts of boards. If you go and get an Arduino Pro, so on Arduino's website, there's a section for Pro. I do believe that all of the Pro boards will let you implement machine learning. So you can go check out the Potentas, the Niklas, and even the Nano 33 BLE Sense and the Nano RP2040 Connect. All of those will run ML for you. STM-based microcontrollers, yes, most of them are 32-bit ARM-based Cortex processors. So yes, they will run that. Marcello, just stop me when I run out of time, please.
No, we are almost there, but we have
we have 5 more minutes. Yeah, that's right.
Okay, great. And then there's a question which says, which ML can you recommend to use in case we want to deploy it on the tiny device? So the answer here is it's not the ML, it's your use case, right? And I think we've seen different examples of what you could do. So first of all, you need to think of the microcontroller and ask yourself, what sensors do you have on the microcontroller and what data can you collect with those sensors? And then you need to ask yourself what problem you want to solve and how the data from those sensors can help you solve the problem. And then you get to the question of whether it's a simple, yes, no binary logic type thing, or whether you need to go to ML. So one of the things that we didn't mention about ML is why we use ML in the first place. And it's simply the case of we use ML when we don't have a simple correlation. We don't know what the correlation is between two things. One of my favorite examples is you don't really need ML to go from centigrade to Fahrenheit if you're converting temperature, because there's a standard equation for that, right? But in the basics of ML, we talk about how do you tell the difference between a cat and a dog in an image, and that's where you need ML because, or even if you think about oranges and apples, it's not really about the color because some apples kind of like are orange. It's not about the shape; they're both round, right? But you can tell if you've held apples for long enough and you've held oranges for long enough, you can tell when you're looking at an apple and when you're looking at an orange, right? And that's because as a human, you've just learned intuitively to tell the difference. And that's where ML comes in. So it's going to be a case of, can I solve this problem using just traditional programming, or do I need to collect lots of data to figure out how to do it? And then Alex asked, could you talk about the type of ML models or techniques which are challenging to optimize and port to currently available microcontrollers, e.g. CNN? Large language models are out of the question, right? There's a reason why it's called tiny. So maybe when we do get to tiny language models, then we can come back here. CNNs, RNNs, so we don't want to focus on the challenges because we don't want to dissuade anybody from, getting things done. So instead, what I'm going to say is tune in tomorrow. Don't miss Sean's session. And he's going to show you how some of the things that we call challenging can actually be simplified. So how you can build an entire ML pipeline using Edge Impulse. So just tune into that. Tiny ML examples to climate change or public transportation. Yeah, I mean, they're everywhere. So climate change, we had, what's their name? But they worked with, I think, Hackstar on some smart weather stations. The Thingy, Marcello, can I remember the name? The manufacturers of the Thingy 51 and the 91.
It's ARM. No, it's Nordic.
Nordic, yes, Nordic, yes.
Nordic Same, yeah.
Yes, so Nordic has, they've been inviting people to take part in challenges for things like smart weather stations. So there are definitely public examples. If you go to Hackstar and you look either on the Nordic or on the smart weather station, you'll find those examples there. And then I think we've got 1 more minute. Can Arduino and TinyML be used to class? Okay, yeah, I've already answered this. Okay, so I think I actually went up. So Marco and Marcello, did I miss any questions that you would love for me to answer in the last 1 minute?
Okay.
No. Go ahead, Marcello.
No, I think it's okay. I just saw one people asking about Raspberry Pi. If it's possible to use, I think. Of course.
Yes, absolutely. So a Raspberry Pi is a single board computer. It's usually way more powerful than the microcontrollers we're talking about. And you can have Raspberry Pis deployed in what's called deeply embedded applications. The difference is that the Raspberry Pi has an operating system. So you don't need to program it the way you program a microcontroller. You'll mostly just remain in the realm of Python versus C and C++ when you're dealing with microcontrollers. But Raspberry Pi, has the interface pins similar to what you have in microcontroller. So you also need to have that strong foundation with electronics in order to be able to deal with things. But yes, definitely Raspberry Pi.
Only a comment, because I think another question asked why we didn't mention a lot Raspberry Pi. The point is we are talking about low power devices, and Raspberry Pi is not a low power device. We're talking about some amperes to run. We need a big battery to run a Raspberry Pi. We can classify Raspberry Pi as mobile phone. It's an edge ML, but not thin ML, something like that. I think that I comment tomorrow.
Yeah, thanks for that. Okay,
yeah.
So I'll stop sharing and hand over control back to you.
Super, thank you very much, Robert. That was an excellent presentation. We had lots of questions. This is great. So thank you so much to all participants. That's exactly how we, wanted a workshop to be, right? Interactive with lots of questions. That's great. Please don't forget to join Discord. We want the discussion to continue on Discord, and Marcello has been answering some questions. Please feel free to just copy your questions on Discord. Robert will be there and Marcello will be there, all the lectures from today. And again, we have a community of over 1,000 people there. So if you have any technical question, then you have very good chances of getting a reply. I think that's all for today. We've been online for 3 hours now. So our colleagues in Asia, that's going to be late in the evening. So thanks a lot for, taking the time to join, and see you tomorrow. Same time, we're going to dive into some more technical examples with Marcello, with other great lectures tomorrow. So have a good evening or have a good rest of the day, and see you tomorrow.
Thanks, Marco.
Bye-bye.
Thanks, Diego, Robert, everyone.
Bye-bye. Thanks.
Bye-bye.